So today we're going to be talking about reaction rates. So when we're talking about rates for reactions, we're talking about the speed of a reaction. In chemistry, we measure that as a change. We use triangle for change, or delta. So a change in amount over a change in time. Okay. And the amount can be measured in a couple different ways. You could do a change in concentration. You could do a change in volume, change in pressure. You could do a change in molarity, change in mass, change in pH, change in absorbance if you're doing in a spectrophotometer. So you'll need to identify the unit of change for the amount there. And then the time unit, the SI unit's seconds, but sometimes you'll see minutes or hours. So just be careful and pay attention to the time unit. But you'll alwathat's have two parts to that unit for rate. I will say the most common one is going to be molarity per second, just because that's what comes up the most frequently on the AP exam. But again, it could be grams per minute, or it could be liters per hour or something. It's just this is the most common. Now again, experimentally, we're going to measure rate by measuring a change, and change in time for sure, but the change in amount will vary based on the particular reaction that you're doing. If the reaction is producing a gas, you could collect that gas. So you can measure the volume of that gas that you produced. You could collect it in a balloon, you could collect it in a syringe, you could collect it over water in a eudiometer. So you can measure the volume. You could also, in a sealed container, you could also track the change in pressure for a gas. But this will both be for gas. Okay. You could also measure change in molarity. That's a little harder to directly measure, but you could use absorbance to measure molarity if you have a calibration curve, and then use a change in absorbance. Use your Beer's law to convert absorbance into concentration and track that over time. You could also do mass, and usually that will just be as simple as if you're producing a gas, you could assume that the gas is evaporating and leaving. If it's not a sealed container, then the mass will be decreasing overall over time because of the gas leaving. So you could track the change in mass over time. And then you could also track the change in pH over time. This one doesn't come up quite as frequently because it has to be a reaction where there is a change in pH from reactants to products. Okay, if you know the rate of reaction or the rate of disappearance for one thing or the rate of appearance for a different thing, as long as you know one of those values, you can use the coefficients from the balanced chemical equation to calculate the rate of disappearance or appearance for another thing. For example, if you know that the rate for HNO3 is 0.0800 molarity per second for HNO3, for nitric acid, you can find and that's the rate of disappearance, because it's a reactant, it's getting used up as over the course of the reaction. So that's the rate of disappearance. Occasionally we'll use a negative value to denote disappearance, but then they usually just say the rate of change of HNO3 was negative 0.08. But then if they say the rate of disappearance, that already gives you that negative value, so you don't really need it. Now, let's say, for example, we want to find the rate of appearance for the copper 2 nitrate here. So you would use the balanced equation. So we have the 3CuNO32 for every 8 HNO3. And then you would multiply and divide, and you get the rate there is 0.0300 molarity per second for the copper 2 nitrate. And that is the rate of appearance because it's a product. So anytime you have rates, you can just use the coefficients. Now, we also want to talk about just the rate of reaction. So in chemistry, sometimes we'll talk about the rate for specific things, but sometimes we'll talk about the rate of the overall reaction. And to do that, I want you to think about, we're going to use that same amount. That's the rate of disappearance of the HNO3. Excuse me. So every time the reaction goes once, every time you have one reaction happen, we're going to use up 8 HNO3s. Okay. And RxN is how we abbreviate reaction. So every one time the reaction goes, you need to use 8 nitric acids. So when you calculate that, you get 0.0100 molarity per second for reaction. That is the rate of the overall reaction. So just be careful with the wording in the question, whether it's asking for a specific species or if it's asking for the reaction as a whole. You can also graph the reactants or the products over time, or both. If you're graphing the reactants over time, the reactants will decrease over time. So you're starting with a lot of reactants, but then notice how the slope decreases, okay? So you have a large negative slope here on tangent to the curve, but as you progress, the slope tangent to the curve is less negative. Okay? And this is, of course, concentration over time, okay, or just amount over time. But you're using up the reactants, so it becomes harder for those reactants to collide with one another and react as quickly. So as you use them up, the rate slows down, and that's important. The most accurate measurement for rate is going to be at the beginning of the reaction, okay? Very beginning of the reaction, because that's when you have an abundance of reactants. So if I were to use this to find the rate, we would pick a point like very early on in the reaction and find a line tangent to that curve, and the slope of that line is the rate. Okay, so that's for reactants. Now you can do the same thing with products, all right? But products will look a little different. The products are going to start at 0. You don't have any products to begin with, and they're going to increase over time. But again, it's going to kind of flatten out because at a certain amount of time you're running out of reactants, so you can't create as many products. So the most accurate measurement for rate, of course, is near the beginning, and again, you'll find a slope tangent to the line in the beginning there. That will give you the rate most accurately. Now, in chemistry, we don't actually do any calculus, or at least in AP chemistry, we don't do any calculus. So you won't ever be asked to find the specific like equation of the line or the slope of the line tangent to a curve. In theory, they could ask you to estimate it, so you could just use a straight edge and graph a line that is close to tangent, and then you'll be close in your answer. But more frequently, you'll just need to know like this part is the most accurate part for rate. You might be asked to explain why the slope is decreasing over time, and that's because you're using up reactants. But you're not very likely to see where they'll ask you to find a line tangent to the curve. They could find, excuse me, they could ask you to find the average rate. So you could pick a point here to here and find the average rate for that time. And we could just do change in y over change in x to find the slope of that line for those 2 specific points. But again, it's not super likely because of the level of math required for the AP chemistry exam. So all of this is based off of collision theory. There's 3 parts to collision theory. And this is describing how chemicals are reacting with each other. And the first thing is that the particles must collide. In order for 2 things to react with each other, they must bump into each other. The second aspect there is they must collide with the correct orientation. So if you have like a really large molecule, you want to make sure that the other molecule that's reacting is colliding with the correct spot. Because if it bumps in over here, maybe it won't react So the orientation refers to that they're colliding in a way that the parts of it, the specific atoms that are reacting, are actually colliding. And then the third aspect of collision theory is they must collide with enough energy. And we call that energy the activation energy. It's the energy required for the reaction to start. So they must have enough energy when they collide. So those are the 3 parts. Then there are 3 things that affect the rate of a reaction based off of collision theory. The first thing is concentration. The greater the concentration, the more likely the particles are to collide. So, and more collisions, greater rate. The second thing would be temperature. Now, temperature affects the average kinetic energy. So, if they have more kinetic energy, they're going to be moving faster. If they're moving faster, they're going to collide more often, and more collisions means faster rate. The third thing will be surface area. And surface area is very reaction dependent, but if you picture like a sugar cube, okay, and you have a bunch of particles in that cube, only the particles on the surface can react with something else, because that's where the collisions happen. But if you were to break that sugar cube up into a bunch of little pieces instead, then there's lots more surface, lots more area where the reactions can happen, the collisions can happen. So the greater the surface area, the smaller the particles, the more likely it will react, the more collisions, the faster the rate of the reaction. And then another thing we're going to talk about is catalysts. Catalysts are substances that speed up the rate of reaction without being used up. I'm not going to call it one of the factors that affect rate, because it's more like it's its own separate concept. You can use catalysts for some reactions to increase the rate, but it depends on the reaction, depends on the specific catalyst. Not every reaction is going to have a catalyst that will affect it. Okay, so here's another example. If I have this reaction, ozone breaking down into oxygen gas, if I have the rate of disappearance of ozone is 0.0034 molarity per second for ozone, what is the appearance of O2? You just use the coefficients. There are 2O3. I can't write today. 3 O2 are produced for every 2 O3 used up. The O3s cancel. 0.0034 times 3 divided by 2 will give you the 0.0051 molarity per second of O2. And this is the rate of appearance of O2 because that's a product. Now, if it's asking for the rate of overall reaction, we need to do it a little differently. 34 molarity per second for ozone. There are 2 ozones used for every 1 time the reaction happens. So if I go ahead and divide that by 2, I get 0.0017 molarity per second for the reaction. So this is the rate of disappearance of O3, the rate of appearance for O2, and the overall rate for the reaction.